Alright, ladies and gentlemen, today we're going to take a look at the second of our conic sections. This family of conic sections is called the ellipse. The plural of one ellipse is many ellipses. So let's take a look first at why they are called conic sections. If you recall, what we can do is make a double cone here. Any way we slice this double cone is going to make a different shape. The shape I have here looks pretty circular. If I slice the double cone nice and horizontally there, end up with a circle. So in order to get an ellipse, all I really have to do is change the angle of the slice, and voila! I have what is called an ellipse. I can change the size of the ellipse by moving up and down. Here's a large ellipse. Here's a smaller ellipse. Tiny little guy there. And that's it. Here's another visual representation of the ellipse. Slice. There it is. The ellipse. Okay, so this is the second of our conic sections. The first was the circle. We defined a circle as the locus of all points a set distance away from a fixed point. That fixed point is called the center of the circle. Here's a visual representation of that. All of these blue points are a fixed distance away from the big red point in the middle. That big red point is called the center, and the fixed distance is called the radius. Furthermore, this circle has an equation associated with it. The equation comes from the Pythagorean theorem, which also is the basis of the distance formula. So if we call this point C and give it the coordinates HK, and we pick some point, any point on the outside of the circle, take this blue one, and we call it XY, then we can define the circle with the following equation: x minus h squared plus y minus k squared equals r squared, where hk is the center and xy is any point on the circle. For instance, if the center of this circle was the point, I don't know, -5, 2, and the radius of this circle was 11, then the particular equation associated with this particular circle would be x minus -5 plus y minus 2 squared equals, I forgot my squared up there, that would have been bad, equals 11 squared, which is 121. Now the ellipse has a similar sort of definition. It is also the locus, it is a locus of points, but the definition is a little bit different. Let's take a look at a diagram here to get a sense of how we define an ellipse. The circle definition was based on the distance from the outside of the figure to one central point called the center. An ellipse is a little different because we have two different lengths that come into play, and these points in the middle are called the foci. We have focus 1 and focus 2 labeled as F1 and F2. The plural of the word focus is foci, F-O-C-I. And here's the basic gist. I can take this point P, and let's swing P around and around and around and around. We have the blue segment, which connects the outside point to F1, and we have the red segment, which connects point P to F2. And the relationship can be demonstrated by the numbers that are changing at the top of the screen here. We have the red distance, and we have the blue distance, and we have the sum of their distances, and as you can see, that sum is not changing. I can change that sum by sliding this other slider here, and let's increase it a little bit. As you can see, if I change the sum, I change the side of the ellipse. Now when I move the point around and around and around, I still have two segments, a blue one and a red one. The two segments connect point P, which is just an arbitrary point on the outside of the figure, to these two mysterious foci. But no matter where I am on the circle, even if I'm all the way almost flat, or even if I'm at the very top here, now the sum is 8. If I change the sum to something very small, well, let's see what this says. In order to have an ellipse, the major axis must be as large as the distance between the foci. Okay, so this is like the smallest ellipse I can get right here. Anything less than this turns out to be impossible. So here's the last one, 5. We're going to introduce some of the basic vocabulary now, but we're not going to get too deep into the mathiness of it. This video, the purpose of this video is more of a general introduction to the ellipse and maybe some of the applications out there. So F1 in this case and F2 are points, and they are called the foci. Okay, and that's the plural of the word focus. P is a point on the ellipse, and there's a couple other terms that we should become comfortable with. Those are the axes. So this shape has a major axis and a minor axis. A major axis and a minor axis. From here to here represents the major axis, and the shorter of the two axes, from here to here, top to bottom, that is the minor axis. And these are pretty much the parts that make up an ellipse. Some of the more famous examples of ellipses in the real world are the planetary motions, for example. The Greek astronomers thought that the planets moved in circular orbits, the first of our conic sections, around an unmoving Earth, since the circle is the simplest mathematical curve. However, in the 17th century, Johannes Kepler, I think that's how you say his first name, Johannes maybe, he eventually discovered that each planet travels around the Sun in an elliptical orbit with the Sun as one of its foci. So let's see if I can do this in red. Here's a random ellipse. Let's see if I can find Earth in there. No, the Earth orbit is going to be too small. So let's take a look at this orbit here, one of the larger outside planets, and that's the ellipse. It has a major axis, it has a minor axis. It looks like the Sun is one of the foci in this shape. Then it looks like the other foci, the other focus rather, is pretty close by, maybe right around there. There isn't actually another planet or another star there, but the elliptical orbit is determined by a focus, a real focus called the Sun, and the other focus is more of a theoretical focus. And this elliptical orbit, of course, has a major axis and it has a minor axis. Let's see, what else do we have? We have comets also go around the Sun in an elliptical orbit. This is an animation of Halley's Comet making its way around the Earth. Not around the Earth, of course, but rather around the Sun. Once again, the Sun plays the role of the focus of the comet's elliptical orbit. I actually had the chance to see Halley's Comet when I was just a youngster. I was probably in the 80s, I believe, and I hope to still be around when Halley's Comet makes its way back around. Again, we can take a look at Halley's Comet, at least the orbit of it. It is an ellipse. The Sun is one of the foci. The other focus probably way over here. There is a nice sort of symmetry, and that one is more of a theoretical focus. There's not actually anything there that determines the orbit of the comet. But this also has a major axis going this way and a minor axis going roughly this way. Some other instances of ellipses. You tilt a glass of water and the surface of liquid acquires an elliptical outline. Salami, everybody likes salami, is often cut obliquely to obtain an elliptical slices, which are larger. Even the salami can be defined as an ellipse. There it is with a major axis. I'm going to guess the foci are right here and right here. Major axis, minor axis going vertically there. Major axis cutting across. One of the more interesting characteristics of an ellipse is its reflective properties. This might help us visualize this a little bit. Any point I pick on the outside well, how do I put this into words? If I were to like shoot a laser beam from one focus, it would hit the wall of the ellipse, and no matter where I go, it's always going to bounce and strike the other focus, no matter where I go. It's pretty unique. There've actually, some clever architects have built this into their architecture. So they built an elliptical room, and one person can stand on one end of the room at one of the foci and whisper something that nobody really else can hear except somebody standing there at the other focus. There's one more. Alright, we can take another look at this reflective property. Instead of individual laser beams, imagine like, I don't know, 1,000,000 laser beams coming out of one of those foci at one time. Where would they all go? Well, it would look something like this. Instead of trying to animate 1,000,000 laser beams, think of it as like an energy circle that kind of comes out of one of the foci. I really have a hard time with that. With one of the foci. Here we go. So there it goes. This energy kind of comes out of the red one, and all of it centers back onto the black one. It can go back and forth, back and forth, back and forth. So this characteristic has been manipulated for human use. What I think is one of the most interesting examples is the use of ellipses for treating kidney stones. So a kidney stone is a deposit that kind of occurs in your kidneys or in your urinary tract. Apparently they're incredibly painful. This is what they look like when they're not inside of you. You can imagine that having these little jagged calcium deposits in your body, in your kidneys, is not a pleasant experience. It causes immense pain, and for many years there was no real good way to treat these things. You just have to do surgery, just cut somebody open and try to remove them that way, and oftentimes people die from the operation. However, a treatment has come along where they bombard the kidney stones with shock waves to crush them. Once the kidney stones have been obliterated a bit, they are small enough to pass out of the body naturally. But how can you focus ultrasound shock waves on something so small? Well, it can be done with something called a lithotripter. I don't know if that's how you pronounce it. Lithotripter, perhaps. This is a fancy looking machine that does exactly this. It focuses shock waves on to very small kidney stones. And the physics, the science behind it, has to do with ellipses. This is the basic gist of it. You set up the machine in such a way that the kidney stone is a focal point of an ellipse. Imagine an ellipse that comes around like this. This is part of the machine. The machine has a reflective ellipse built right into it, and the shock waves come out of a thing right here, and just like in the video, the shock waves emanate from one focus and focus right on the kidney stone, hopefully obliterating it. One other look at this mechanism is right here. This is done with a whoops, there we go, a spark plug, brass ellipsoidal reflector, and every single one of these energy waves, or whatever you want to call it, is going to focus on this point right here. So ladies and gentlemen, that's kind of an introduction to ellipses. I hope you've enjoyed the presentation. Have a wonderful rest of your day.